So this is going to be our first technical talk. It's really meant to kind of flatten the playing field. We often have people from very different backgrounds. Sometimes we have participants who don't actually have background in biophotonics. So on some level, this will be very, very basic and fundamental. And, we have PhDs in physics here. So, pardon me, I'm not a physicist. I'll be maybe a little too casual in presenting some of the concepts here. But it's really just to provide the foundation for the rest of the 2 weeks. And many of the concepts and themes you're going to see revisited in different guises in lectures throughout the course. Again, I have less than 50 slides. We have a fair bit of time. I'm going to try and go slow. I want to make this conversational. And hopefully, for those of you who have a lot of expertise in biophotonics, it won't be too boring. So I always try to start my lectures with kind of teaching objectives or outlines. Kind of by the end of this lecture, you should be able to address each of these issues that we'll be discussing. So obviously, biophotonics, is a broad field, encompasses a very large range of techniques. We use light to probe biological systems on the sub-micron scale, all the way to the organ scale, right? So you're spanning several orders of magnitude. And if we want to gain some insight and understand how light interacts with tissue on multiples across these spatial scales within a given domain, you may have to consider various approaches or different approaches to modeling light propagation across those scales. So we're going to talk about, if we think about multi-scale biophotonics going from the sub-micron scale to the centimeter spatial scales, what are the approaches one might need to consider when modeling that light propagation? And within any particular approach, each approach has a limitation and range of applicability. So we're going to try to talk about that within some sort of coherent framework. The other thing is that, often you can divide biophotonic applications to therapies, where you actually use the light to create some change within the biological system. And so there you're really interested in creating or engineering a light field within your biological sample to create the change that you want, that often you want something very specific and very targeted, versus diagnostic applications where, of course, you're generating a light field within the sample, but you're typically limited to where you sense that light because you can only see the light that escapes the sample, unless you're putting in a probe inside the tissue to capture it. And so in terms of modeling and computation, there are various slightly different aspects that you need to consider, although there's actually an interplay between, say, the volumetric light field and what you sense at the surfaces. So although we will be spending a day on microscopy, the bulk of this course really is looking at probing tissues on the, say, tens of microns to millimeters to centimeter spatial scales. And in those contexts, and we'll talk about why, and in those contexts, we typically deal with light not as a wave propagating through the sample, but as a neutral particle propagating through the sample. And this is the field of radiative transport. That's what Monte Carlo simulations essentially simulate, is this transport of neutral particles through a medium. And kind of the fundamental metric within radiative transport is this thing called the radiance. And it's actually a 6-dimensional object, because if you want to define the transport of neutral particles in a medium, you have 6 dimensions. You have a location in space, which is 3 dimensions in Cartesian coordinates. You have time, because obviously you can have a temporally varying source, so that's 4. And then you have directionality, because from a given point, the light can travel in any direction. And so the most efficient way to parameterize that is direction around a unit sphere. So you have polar coordinate and you have an azimuthal coordinate. So this is a six-dimensional object. And essentially that's what we have to solve if we want to have a complete description of a light field in a volume. And then what gives rise to that radiant field is essentially how the light interacts with the material, right? And we're going to be dealing with cases mostly where we're going to just, for simplicity, consider a single wavelength, and that we're not going to consider non-conservative scattering. So we're going to, forget about inelastic scattering for the moment. Just think everything is staying at the same energy. And so all we're concerned with is absorption and scattering, linear absorption, linear scattering. And if you're treating that in a rigorous way, you can then develop an equation called the radiative transport equation that, if solved, can give you a complete solution to the radiance in your medium. And so we're going to talk about that conceptually. So those first 1, 2, 3, 4 bullet points will be roughly the first half of the lecture or so. And then, in order to solve such an equation, you have to be able to represent the tissue optically, right? And so we're going to talk about optical properties of tissue. What are the origins of those optical properties? What are the characteristics of those properties and their spectral dependence? Because ultimately, if we're, at least in diagnostics, if we're interested in understanding composition or structure of the tissue, ultimately, those are derived, or they arise from a certain optical arrangement or optical property of the tissue. So there's a mapping from these kind of optical properties of tissue to what we may be interested in physiologically. And this interplay between light transport and the spatial scales and temporal scales associated with light transport and your tissue optical properties give rise to characteristic spatial and temporal scales for light transport within the domain. And we'll find as we go through the course that these spatial and temporal scales really inform the situations where certain techniques work well, as well as certain situations where they don't work so well. And that, again, that'll arise. You'll see this interplay as the course goes on, but at least we'll have the foundation here, and we'll repeat certain concepts going forward. So hopefully at the end of this lecture, you'll have a good sense of these, and we'll definitely revisit these. Okay, so starting very basic, I'm going to be doing things that maybe you saw in high school. So just a reminder, right? Light can be thought of within two kind of constructs, kind of rigorously in a classical sense. Light is a transverse electromagnetic wave, right? So you have light travels in a direction, or propagation direction, and there are oscillations both in electric field and magnetic field, which are mutually orthogonal to that propagation direction. So what we're doing is that we're, oscillating an electric field. So if you're stationary in space, that object is feeling an oscillation in an electric field as the light propagates through. And the distance between, two identical points along that field, along the propagation direction, defines the wavelength, okay? Now, you can also think of light in terms of a neutral particle description, so photons are localized but massless quanta of energy, right? And associated with a given wavelength is a photon energy, right? And that's parameterized both through its frequency and Planck's constant, or you can also represent it through wavelength parameterized through the speed of light, c. Okay, so you can ascribe an energy to each photon based on this parameterization. Okay, and that becomes informative or helpful when trying to understand how the light interacts with a medium. So it's also helpful to kind of think about, typically we use, visible near infrared, now shortwave infrared light in biological media, but it's good to kind of think about the light that we typically used in in biophotonic applications relative to kind of the entire electromagnetic wave spectrum. And what's really, in some sense, unique or special about visible near-infrared light is that the spatial scale of the wavelength really matches a lot of objects of biological interest in terms of spatial scale, right? So we're right around the size of, from several hundred nanometers to a few microns. And you see that things that we're interested in, maybe molecular objects are much smaller, so proteins, lipids. The molecules themselves are maybe 100 times smaller, but as you get into, cellular organelles, entire cells, extracellular matrix, you kind of span this kind of tens of nanometers out to tens of micron spatial scale. So in some sense, the spatial scales over which you're exciting biological systems through the oscillation of electromagnetic waves is in some sense almost resonant in some sense with the spatial scale of the things that you're interested in probing. Okay. And so, so these match the spatial scales of subcellular, cellular, and extracellular tissue structures. The other way you can think about this is the energetics of this. I just mentioned that you can ascribe an energy to each wavelength of light. This is typically expressed in terms of electron volts. And what's interesting is that when you're from kind of the visible blue out to the near IR, that corresponds to high energies in the blue, approaching 2-3 EVs. And then you go down in energy as you move towards the red near infrared down to 0.7, 0.5 EV. And what's interesting about this range of energies is that these are energies that either as you go towards the blue, more likely to excite electronic energy levels within biomolecules. And then as you go towards the red near infrared, you start exciting vibrational modes in the tissue. So you're really probing, you have the opportunity, especially if you do spectroscopy, you're probing the fundamental electronic and vibrational characteristics of biomolecules. And that's where kind of the functional aspect, the compositional aspect, you gain a lot of information and power. And what's interesting is that if you think about this in the global scheme of, or a global context of medical imaging, if you go further out, if you go beyond the infrared and you go towards, you may have heard of terahertz or microwave imaging, there you're starting to probe rotational energy levels in biomolecules. If you go towards ionizing radiation, you go to soft X-rays or whatever, there you're actually probing direct atomic properties of matter. And actually we have a professor here, Chris Barty, who actually has come up with a way to actually produce monochromatic X-rays. Usually the X-rays you get in like the medical office is actually a very broad spectrum. You can do much more monochromatic X-rays, and you can do like elemental images of the human body. You're very targeted and has very strong promise for medical applications. So it's nice to think about the wavelength of light and matching spatial scales of objects that we're interested in probing, and also the energetics. So you're in this very unique place in the electromagnetic spectrum, and that's, to give you insights into electronic and vibrational modes. Okay, so let's talk about spatial scales a little bit more. Often in the field, we think about, spatial scales. For simplicity, I'm going to talk about a microdomain, a mesoscopic domain, and a macroscopic domain. And we have a range of biophotonic applications that are uniquely, that have characteristics that uniquely probe biological targets across these spatial scales. Of course, probably the first usage of light in biology has been just classical bright field microscopy. Didn't give you great contrast, but even back in the 19th century and early 20th century, there was a fair bit of work in that area. Things like phase contrast and And DIC microscopy came along, but basically you're able to start to probe or image biological samples, thin biological samples, down to sub-micron resolution, but you can't go very deep. Of course, now with the advent of multiphoton microscopy and a second harmonic generation, coherent anti-Stokes Raman spectra, they're very sophisticated techniques where you leverage nonlinear processes within the biological sample, and you're able to make sure that you produce light by the sample that's localized to kind of nanometer scale volume, so that whatever light you emit, has come from a very small volume, because you're relying on nonlinear processes. And those nonlinear processes can only be excited efficiently in a small volume where the intensities are sufficiently high. And so we'll talk about, actually, I can't remember, tomorrow or the day after, we're going to have a day focused on microscopy. But there you're relying on producing a coherent wavefront of the light to generate, certainly in bright field and phase contrast, you're actually leveraging the coherent properties of the light to image, or you're leveraging the coherent properties of light to excite nonlinear optical properties. So you really need coherence to be able. So as you allow light to propagate further and further in tissue, you start to lose the fidelity of that coherent wavefront, because scattering starts to, aberrate that wavefront. And so this has the detriment that you're unable to really probe tissues quite coherently. But things like OCT use interferometric techniques to essentially isolate only those photons or those elements of the light that retain coherence with a reference. And so it's a way of filtering or gating light that maintains interference, coherence, diffraction effects to get fairly good resolution in terms of spatial resolution at moderate depths within tissue. Because as you go deeper and deeper, there are just fewer photons available that retain that coherent nature, because scattering tends to disperse the light, and the optical phase relationships of the light that you're collecting are kind of destroyed. As you go deeper, and you're okay with tolerating lower resolution, you can look at various, you still leverage interference in some way. You can get kind of incoherent but interference patterns that are based on speckles. So, if you take a laser pointer, you shine it on a piece of paper, you'll see areas that are brighter versus darker. And that is typically, or you do it on sheetrock on a wall, you'll see a non-uniform, very speckly spatial pattern. And that speckly pattern tells you something about the morphology of the tissue. That's usually a static speckle. But if you have flow, that speckle will change based on the flow and the movement of the targets in the tissue. And so speckle imaging allows you to go a little deeper, but you're leveraging coherence, but not in a kind of spatially organized way. You rely on correlations, either temporal or spatial correlations of that interference pattern to figure something out in terms of the structure and function of the tissue. So you're going from, loss of resolution from the submicron spatial scale for, microscopy techniques to kind of tens of micrometers. But if you allow the light to propagate even further, or you're collecting light that has propagated further, at some point you lose the optical phase relationships between the tissue. And so this is where going from a wave-based framework for modeling light to a particle framework makes sense, because you really no longer have any coherence maintained in your light signal. The optical phase relationships are completely scrambled. And so you lose resolution, but you gain in potential information because the optical path lengths allow you to become sensitive to the absorption of biomolecules. And so there are techniques such as SFDI, spatial frequency domain imaging, allows you to look at moderate depths, several millimeters, with resolutions on the order of 100, 200 microns. What's interesting in this domain is that even though optical phase relationships are scrambled, they're still often we use, laser sources, which have strong directionality and information. So even though your optical phase relationships are destroyed, there's actually still some strong directionality in the light field. And we'll talk about radiance in a bit, but you don't necessarily, if you look at superficial depths in the tissue, say less than a millimeter, if you're looking at the sampling the light field, you have strong asymmetries in terms of the direction from which light is emanating from a given point. But if you then let the light travel even deeper, so much scattering occurs that actually, if you sample the light emitting from a deep point in the tissue, it has no preferred direction anymore. Okay? And so when you go from a place where you've lost interference, lost coherence, but you still have directionality, typically we talk about that as the transport regime. So you've gone from an electromagnetic wave context and you go to radiative transport, you're dealing with particles, but you still have to worry about the directionality of the light. But if you undergo further scattering and you lose directionality of light, we typically refer to that as the diffuse regime, and that's the field of diffuse optics. Okay, and those are things like diffuse optical spectroscopy and imaging. So both transport regime and diffuse optics, you lost the wave character of light, but the main thing going from transport to diffuse is losing directionality. And when you lose directionality, actually, implies certain things from a modeling and computation perspective, which we'll talk about. Okay, and so from a modeling perspective, if you have a situation you need to handle that your imaging technique or your application leverages coherent properties of light, you must use Maxwell's equations to model that phenomenon, right? Because it is a rigorous, as we know, it's a rigorous framework to handle polarization, interference, diffraction, coherence. But as you lose those wave properties, you can go to what's called the radiative transport equation, which is a particle-based formulation for light transport in a medium that both absorbs and scatters light. The radiative transport equation, as I've said already, it handles the spatial, temporal, and angular variation of light. It's rigorous within the particle context. But it's not a straightforward equation to solve. And Monte Carlo simulations, at least within our field, have taken kind of is now considered the gold standard for solving the radiative transport equation, but it is also very computationally expensive. But when you lose directionality, actually you can simplify the radiative transport equation to something called the diffusion approximation. So the diffusion approximation allows you to solve the radiative transport equation approximately, but you actually can get analytic solutions, and you can implement it within, say, a finite difference or finite element solver, which is much more computationally efficient and is sufficiently accurate when you're probing large tissue volumes on the centimeter spatial scale, and is used quite a bit. So, and kind of the spatial scales over which you transition from kind of the wave formulation to radiative transport to diffusion is parameterized by these three spatial scales. So Maxwell's equations, obviously the fundamental spatial scale involved there is the wavelength of light. And as you propagate and scatter over multiple wavelengths, that's when you start to lose coherence. And the characteristic length scale in which radiative transport is operative is what we call L sub s. And L sub s is a spatial scale that is linked to the mean distance a photon travels within the tissue before it gets scattered. that tends to be on the single to tens of microns. And then the loss of directionality occurs after you've undergone multiple scattering events. And that's given by what's called the transport mean free path, L star. And we'll talk about those in more detail in just a bit. So let's talk about Maxwell's equations a little more deeply. Maybe I should, before getting into the details, are there any questions at this point? Yes.
So the micro is like wave-based, and then you said you're going particle-based with meso, and then for macro, it's what's
We lose, okay, so here, once you lose coherence and interference, the wave front gets sufficiently aberrated and dispersed, you can go to a particle-based. Then and we call this the transport regime. But once you scatter even further, the photon has lost any memory of its initial direction. Often we use collimated sources. All the light we're injecting in the tissue is traveling in one direction. You can have some scattering, but the light field is still strongly influenced by the initial direction of injection. But if you encounter a sufficient number of scattering events, the photons undergo tens, hundreds of scattering events, the light field is no longer influenced by the directionality of the light coming into the system. And that's when you're in the diffuse regime. And that's given by the transport mean free path. And I'll give you more rigorous definitions for these parameters in just a bit. So first you have loss of coherence and then loss of directionality. Okay, I think that's the best way to kind of think about it.
As to cases, you are always in the corpuscular.
You're in the corpuscular, the particle, yeah, regime. That's right. Good questions. Other questions? Okay. So let's talk about Maxwell's equation. So, as I've already implied, it's a rigorous classical model for electromagnetic wave propagation. It models all wave phenomenon rigorously within a classical framework. Interference, diffraction, polarization. It's actually, if you could apply Maxwell's equations over large spatial scales, that would be the go-to thing to do. It is, in a classical framework, the most accurate way. But there are challenges. Obviously, the reason why we don't use Maxwell's equations on spatial scales of millimeters to centimeters is, number one, kind of the two properties that govern propagation of light in a wave context are these two parameters called dielectric permeability and dielectric permittivity. And actually, knowing the values or being able to ascribe values for these parameters in a heterogeneous biological tissue is not well known, and then much less known as a function of wavelength, right? So ascribing, and these are related to the refractive index or the complex refractive index, but it's actually very difficult to get at these ideas, at these parameters, and you need to parameterize them. Actually, if people are familiar with Maxwell's equation solvers, you need to actually, in order to get stable solutions to Maxwell's equations, generally, you need to be able to ascribe properties on a spatial scale of maybe 1/10 of the wavelength. Okay, kind of the classic way to solve Maxwell's equation is using a technique called finite difference time domain methods. And you're basically marching the wave at very small wavelength increments, and you have to fully parameterize and describe the system on that spatial scale. So as a result, modeling propagation in scattering media is enormously computationally expensive, but it has been applied to small tissue volumes. And so I guess the leading groups in this domain have been Vadim Bachman at Northwestern, Andy Dunn at UT Austin. He's done a lot of work in this area. Snow Seng in National Taiwan University. We've done some work in this area, introducing kind of some computationally more efficient methods, but in more simplistic systems here. And Jonica, who you'll hear from later on, has done some work. Okay, so Maxwell's equation is really limited to small tissue volumes. So let's go to the radio transport. So radio transport treats light propagation as transport of photons. It can actually be derived from Maxwell's equations under two limiting assumptions. The first thing is that you have, in radiative transport, you have discrete particles that occupy your volume that are responsible for scattering the light. And you have to assume that each of these objects that are scattering the light are sufficiently distributed such that every scatterer lies in the far field of the other scatterer. Because if you look at Maxwell's equations rigorously, if you have a plane wave interacting with a scatterer, in the near field, roughly in the first, say, 6 to 10 particle diameters, the scattered wave is actually evolving with space. Okay? But if you get sufficiently far away, you then get a stationary wave that then travels. So, so both the angular distribution of scattering and the intensity of scattering evolves with distance when you're close to that particle. Radiative transport can't handle that. It can only handle one static distribution of scattered light from these particles. And so you're assuming that all the particles are lying in the far field of the other particles. So that's a fundamental assumption in radiative transport. The other thing is that we're assuming that we're in a random medium, that the particles themselves are not organized or arranged in a periodic way. Because if you organize the particles in a periodic way, you can actually drive interference in a spatially organized way, and then you can actually get coherent propagation. So, you may know even in your lab, you have dielectric mirrors, right? The mirror isn't actually a reflective surface. It's actually variations in refractive index that are periodic with the wavelength of light. So you get an etalon effect, and you get this kind of constructive interference that re-radiates the light backwards and acts like a mirror. So you can't have particles that are organized in any way. You must have a random medium. It's unlike, Maxwell's equation. This is a scalar model. So you're just determining what are the numbers of photons that are emitting from a given point at a given time in a given direction, and cannot predict rigorously interference or diffraction effects. And you can, in some situations, handle polarization. In the radiative transport, there are these things called Stokes vectors, which are parameterizations of the parallel and perpendicular components of the electric field. And you can actually, if you can you understand how the different components of the Stokes vector get scattered or absorbed, you can handle polarization. Well, I'll show you that equation a little later. We won't spend much time on it. But there are some applications in polarimetry, especially for glucose monitoring, that leverage polarization-sensitive Monte Carlo. Okay. Any questions on these assumptions? Yes, Hector. Yes.
So I guess there's some time between the moment when the plane wave interacts with the particle and transits from the near field region to the far field region.
Yes.
Do you have any idea about the time scale or time range for that?
So typically we think about this in terms of, so let me kind of go back. We're going to talk about this. So in the framework of me-scattering is a electromagnetic Maxwell's equation-based framework for computing scattered waves when a plane wave impinges on a spherical particle. And you compute something called the scattering amplitude matrix. And the scattering amplitude matrix actually evolves with space when you're within roughly 10 particle diameters. Once you get beyond roughly 10 particle diameters, it no longer evolves. Okay? So if you have another scatterer close to that, then you better understand how, number one, what is the angular variation of scattering and the intensity in that near field. Radiative transport only utilizes one distribution for the angular distribution of scattering. And so that's where it breaks down. Okay?
Mm-hmm.
Okay, good. Is there a question here, Yijin? No, okay. Good question. Okay. So, like I said, radio transport equation is you're going to see the equation later. It's you know, it's solvable, but it's computationally expensive. So if you let the light propagate further, you lose directionality. You can actually do an approximate solution to diffusion to the radiative transport equation. That's called the diffusion approximation. So the standard diffusion or PN approximation is an approximate solution to the RTE, and it's formed by the expansion of the radiance of the solution in Legendre polynomials. Legendre polynomials is a orthogonal basis set. I know, people who've taken partial differential equations, you do the functional expansions. It is a set of polynomials that are normalized on the unit sphere. And it gives you only azimuthal variation. So you can only change polar angle, but not azimuthal angle. So it assumes that the azimuthal distribution is uniform, but you have variations in polar angle. And it basically imposes a smooth variation in the angular distribution of the light for low n values. But you can transform the radiative transport equation into a closed set of n+1 coupled partial differential equations. Typically, the field has stopped at P1, which means you get just two coupled PDEs, which you can then reduce to one equation. And the standard diffusion approximation or P1 approximation, they're slightly different. We'll see that later on in the course. They have a long history, of development and usage of biophotonics. All the early applications of diffuse optics use the standard diffusion approximation. And they're highly accurate. They're pretty accurate in highly scattering media, right? The important thing is that you have to be on spatial scales where the light has lost its directionality. And so you need to be on spatial scales where you've allowed the light to scatter sufficiently, and you have to be away from sources because the sources themselves are often collimated, or boundaries, because if you have boundaries of refractive index, you get total internal reflection, which is non-isotropic. And so, has angular variation. So you have some challenges for dealing with boundaries. Okay? Okay. Any questions here? Okay. So, I think probably all of you have seen, versions of this slide before. So, you gain, as you gain in depth of probing, you lose in resolution, and you lose in resolution primarily due to the dispersion of the light and the loss of coherence of light, right? And so it's very nice to kind of think about where these domains of light propagation, where you retain the coherence of light, where you retain directionality, and then when you lose both coherence and directionality. So you lose certain levers in terms of probing the tissue, but you gain in terms of depth of probing as you go to the diffuse regime. And then it allows you to probe different spatial scales. Okay. Okay. So now I'm going to talk a little bit about therapy versus diagnostics. Everyone probably at some point has shown a flashlight on their hand or a laser pointer in their finger. Of course, anyone who's been to urgent care or the hospital, they'll put a pulse oximeter on your finger. And so this is just diagrammatically, what a light field might look like if you're, putting a red laser pointer on your finger. And I'm using this as a way to illustrate the differing considerations you may have when you're perhaps interested in a therapeutic application versus a diagnostic one. So, often people may have not been familiar with this term called radiance, but I think more of you maybe have been familiar with the term fluence, right? So fluence essentially tells you it's a metric for what is the total amount of light that's being emitted from a given location in the tissue. So again, just, very cartoon-wise, you can imagine that this is a color bar of the intensity of the fluence in my finger due to that collimated light source. and you may have some spatial decay along the center line of the illumination. And this is what's relevant for either therapeutic applications. So in a therapeutic application, you're using the light to either drive a temperature difference or activating some photosensitive compound, right? Is the ability to activate that compound depends on the amount of light that's available to do that photochemistry. And it's also relevant when you're doing fluorescence. There are many of you that are very interested in using Monte Carlo for fluorescence, right? And that's because obviously you're not going to get fluorescence if you're not exciting the fluorophore, right? So your ability to excite the fluorescence depends on the amount of light that's available in that location, right? So the first step in actually modeling fluorescence emission is first defining what's called the excitation field, okay? How much light do you have available to excite your fluorescence, okay? So you're very interested in both therapeutic and fluorescence application. What is the volumetric distribution of light within your tissue? Okay, and the efficacy of those applications really depends on that volumetric light distribution. Now, in diagnostics, you know, it's not like you don't care about what happens here, but you're only limited to looking at the surface, right? You're only, you know, in a pulse oximeter, you don't even image, right? You just, you know, what is the total amount of light coming out the other side? But, you know, in imaging applications, you may have access to the spatial distribution of the light, either reflected back or transmitted through the finger, right? And so you're only limited to measuring that. And then you want to infer something about what's in this volume. So what's interesting is that these are two different light fields. Obviously, you're interested in either reflectance or transmittance or both. In diagnostics, you're interested in the internal fluence light for the other. But there's an interplay between the two, right? So number one, if something changes within your volume, you know, if oxygenation changes or the blood flow changes or something changes, then it's going to impact the internal light field, and it's going to impact, of course, what you measure in reflectance or transmission. And conversely, if things at the boundary change, it will also change the internal light field. So how might the boundary change? I mean, this is something you can do in the lab, right? You know, you can put your finger and you can put, say, a black absorber on the bottom of your finger. So that means every bit of light that comes out will, and you index match, for instance. So that means every photon that arrives at the bottom of your finger is going to escape and get absorbed, and that will change this light field because you're not allowing total internal reflection to occur here. So there's an interplay between what happens at the boundary and the internal light field and vice versa. Okay, so those are linked. And so the question then is that, well, how do we model this? How can we understand how the propagation of individual photons give rise to these light distributions, and what are the parameters that affect these trajectories? Okay, so again, I'm going to do this very casually, just from a conceptual perspective. You know, so let's just think about a collimated source, you know, that we use to irradiate a tissue that is comprised of scatterers, absorbers, and even fluorophores. So you can imagine that there are a couple things that can happen to a photon. A few things. One is that, you know, if there's a refractive index mismatch, some light won't even enter your tissue, right? You'll get a specular reflection. You can have a photon that enters the tissue, but rattles around, hits a few scatters, then comes out. That's often termed diffuse reflectance. It doesn't mean that the light is completely diffuse from an angular perspective. It just means that the light entered the tissue, interacted with it, and came out the top, okay? As opposed to specular reflection. You can have light that rattles around and then gets absorbed and maybe just generates a temperature change. You can have light that scatters around and comes out, transmitted. And sometimes you can also generate fluorescence. Okay? But from an energetic point of view, at a given wavelength, you know, if you say you're putting in, I'm just going to say a funny number, 100 photons per second, coming in, I naught, and you measure the rate at which photons are specularly reflected, diffusely reflected, absorbed, or transmitted, you have to conserve energy, right? So that sum has to be met. And then if you do, if you imagine putting hundreds of thousands of photons in here, you're going to have some sort of light field. And this is, a diagrammatic representation of the light field in one slice of the tissue, right? It's a 2D representation, but of course it's a 3-dimensional distribution. And you can imagine that if you're looking at one location here, just intuitively, there's going to be a non-uniform distribution of light emanating from that point, right? You're still fairly close to the source. There's probably more light going in the forward direction than the backward direction. There's probably more light actually being kicked to your right versus to your left, right? You can just see that from the spatial gradient. There's a stronger gradient in this direction than in this direction. So there's a non-uniform spatial distribution of light in that material. Of course, as you go further and further away and it undergoes more and more scattering, that directionality is lost. And of course, this is a 3-dimensional distribution, right? I'm just giving you the slice along the plane of the screen. There's also light coming out of the board, and there's light going towards the wall as well. So that's what we tend to think about. If you want to characterize the full angular distribution, you can think about a unit sphere centered on that point, and you can look at the brightness of that sphere is non-uniform because you have different amounts of light going in different directions. So that's why the number density of photons within the tissue or emanating from a different location in the tissue depends on both the space and the direction. And then, as I've already mentioned, the primitive radiative transport quantity is radiance, and it has very interesting units. So it has power per unit area, cross-sectional area, per unit steradian. Steradian is a unit of solid angle, and I'll talk about that in just a second. So it's like an intensity, but resolved with angle. Okay. Any questions on this? Yes.
Do we have any physical analog of those particles? Like, what could they be?
Oh, well, okay.
Concepts or?
Well, I mean, there are, okay, from a rigorous physical description, your tissue has different constituents that have different refractive index. So in a wave description, which is the most rigorous description of this, not a particle-based description, is that you have a coherent wavefront going through a material that has constant variation in space of refractive index. And that starts to aberrate your wavefront. And so in some sense, there is not a direct physical mapping from the wave framework of how you would represent tissue to what a particle framework would. But we think about this casually more like, well, you've got a tissue with cells. Cells themselves are 10 micron objects. They have, different refractive, but within the cell, you have organelles, you have nuclei, mitochondria. All of these have different refractive index, and they have different sizes. And then even your extracellular matrix, the collagen, elastin, they come in different shapes and sizes and have different refractive index. So you can think of those, of course, I'm simplifying it into colors and spheres, but there are objects that you can think from a particle perspective that would scatter light.
Do we have a size limit that this model can apply to, like for those particles?
As long as you can represent the angular distribution of scattering, you can handle it within a radiative transport, as long as you meet those assumptions that I mentioned earlier, that each particle lies in the far field of the other, and there's random distribution. So that's one thing that's actually quite important. Radiative transport, you have to be very careful if you say want to propagate, if you want to say model transport of light through muscle, for instance, because muscle has fibers that are oriented, or tendon, so you have strong angular anisotropy, and you can do things to handle the angular variation of optical properties. But, typically we're assuming that the tissue is structurally isotropic. Okay. Did I address your question? Okay. Other questions? Okay. Okay. So let's talk about, remember, we're going to first think about how those light fields get established, and the two fundamental processes, right, that govern the propagation is absorption and scattering. So this is, again, high school physics. So again, I'm going to use the radiance here. I'm not going to worry about time variation for the moment, and just say that you're radiating a cuvette filled with an absorber, but no scattering in a given direction, right? And you want to see how much change of light you're going to get upon traveling a differential distance, ds. And so this is kind of classic. The change in the amount of light available after propagating a differential thickness, ds, is just given by the amount of absorber you have, we'll call that mu a, times the amount of light that you put in, right? And then you do, elementary calculus, you go dl over L equals minus mu a ds, and then you integrate, right? And you get the classical Beer's law, right? And so this tells you that upon propagating a given distance s, you're going to decay, the light is going to decay exponentially according to the amount of absorption you have in that material. And in our field, this is mu a is called the absorption coefficient. It has units of inverse length, okay? And the key thing here is that once the light is absorbed, they're extinguished and it no longer propagates in the tissue, at least not at that wavelength. In tissue, if you think of the whole visible to near infrared wavelength, the values of mu a can span actually very large spatial scale. So in the near infrared, anywhere from 700 to 1,000, you actually have very, very low absorption. Hemoglobin doesn't absorb much. Water doesn't absorb much. Lipid doesn't absorb much. You have very low absorption. It's like 3 × 10⁻³ millimeters on that order. It depends on tissue. But then if you go out to 3 microns, where water has a high absorption peak at 2.94, you go to 10 to the third per millimeter. And what that means is that if you take the reciprocal of this, I always like to think about the reciprocal of mu a, because the reciprocal of mu a gives you a characteristic spatial scale over which light can propagate before being absorbed. And you see it spans, in this wavelength domain, it spans a huge multiple, what is that? Almost 6 orders of magnitude, right? So if you're at 2.94 microns, in tissue, basically light can propagate about a micron or two. So erbium YAG lasers are often used in surgery if you want very precise surgery. And then, but if you're in the near infrared, then you can propagate, without loss due to absorption, you can propagate, 30 centimeters, right? But of course you have scattering that gets in the way. And so you don't get 30 centimeters deep, you disperse laterally, okay? So this I'm sure is familiar to all of you. In scattering, you actually can develop the same Beer's law. Just think about, I say I have light coming in, impinging in a planar wave at this direction, and I want to see how much light is still traveling in that same direction on the other side. And you get the exact same Beer's law, right? The loss of light traveling in the same direction is linked to the density of scatterers times the amount of light I put in, get the same Beer's law. Now, the thing is that the light isn't gone. Unlike absorption, where the light undergoes absorption, it's gone. This light is still there. It's just traveling in a different direction. And that's where the challenge comes. How do you then track those photons? Okay, and that's where the RT comes in. So again, the scattered photons continue to propagate, but in different directions. We'll call them omega prime. Okay, those are the different directions the light can propagate in. But if you look at the total attenuation of photons traveling in one direction for a differential distance, it's an exponential. I put mu t here, which is just the sum of mu a plus mu s. Okay? And in tissue, in the visible to near infrared, the scattering values are not as broad as in absorption. Roughly, your scattering coefficient is anywhere from 2 to 200 per millimeter. And that corresponds to single scattering lengths. We usually refer to LS. You may remember LS from that slide where I showed Maxwell's equations to radiator transport to diffuse. That's kind of gives you the spatial scale over which you go from Maxwell's equation to the transport regime, 5 to 100 microns, typically, in tissue. Okay? Depends on the tissue, depends on the wavelength. Okay, so now we got to put all these together. And so we got to, make sure that whatever governing equation we adopt handles the extinction of light due to absorption and handles the redirection of light due to scattering. And that's where the radiator transport equation comes in. And it's a scary equation, but I want to emphasize the physics, okay? So how is this equation formulated? So let's just consider this location in the tissue, okay? And we are trying to understand how does light come into that location and leave that location. And we want to look at it at one direction. So let's just say this is direction omega, okay? Coming in and going out. So I'm sitting at this location. I want to know what is the time rate of change of light emanating from that location in that direction, okay? Not in all directions, just in one direction, omega. Okay. One thing I've done here is that I've divided the whole equation by v, which is the velocity of light in the medium. Maybe a more physical way of doing this is actually getting rid of this v here and putting v in front of these, because the velocity is the movement of light. It's the rate at which photons are flowing, okay? So if you look at the time rate of change, what can give rise to the time rate of change of light at that location? Well, first of all, photons are never static. They're always moving, right? So if the light is increasing in time or going down in time, it's because it's either moving away, more light is moving away than coming in, or vice versa. And you can understand that by looking at the gradient, right? If the gradient is going down, that means more light is going away than is coming in. If it's going up, that means more light is coming in. So this is the spatial gradient, the local spatial gradient of the light field. And that's a gradient, as you know, is a vector, right? It gives you the spatial variation of light. But we're only interested in the variation along omega. So we take the dot product of this gradient onto the direction that we want, okay? And so this is the loss of light, it's negative, loss of light due to streaming or due to propagation away from that location, okay? Okay, so that's one way. Just from propagation, you can lose light or you can gain light. The other thing you can do is that you can lose light due to the interaction of the photons with an absorber or scatterer in that location, right? So if you have absorption mu A, the light's gone. If you have scattering, the light is gone from direction omega, right? Because it's gone to another direction, omega prime, okay? So this is just mu t is the sum of mu a and mu s, so you lose there. Now you can gain light, right? You can imagine, well, there could be photons that are coming from other directions, scattering there and get scattered into the direction you're interested in. And that's what this integral term represents. It says, okay, what is the amount of light coming from all of these other directions, mu a? Omega prime. And then, okay, if I have a certain amount of light coming in from omega prime and they're here, they come here, what is the probability that light traveling from omega prime gets scattered into direction omega? Okay, and that's, in our field, that's called the single scattering phase function. It has nothing to do with phase, it has to do with the angular distribution of light. It's a probability density function that lies on the unit sphere. Okay, and then you have to consider all the other directions in which light can propagate into that point and get scattered into omega, right? There's not only light coming in from here, it's coming in from here, coming in from here, coming in from out of the board. You have to integrate over the whole unit sphere. That's usually referred to as 4 pi steradians, because a unit sphere has a surface area of 4 pi, right? And I'll show you shortly how you do that integral. And then in order for that transition to occur, you actually have to have scattering at that location, right? If there's no scatterer at that location, then it's linked to the density of scatterers in your medium, right? If you have no scatterers in the medium, then you're not going to have that opportunity. Okay. And then, of course, you can have sources of light within your material, right? You can have fluorescent source, you can have an interstitial source that is injecting light in your material at a given location in a given direction, because you can have a collimated source or maybe a lens source or a diverging optical fiber that has a numerical aperture. And of course, that source can also go on and off, right? So you have temporally modulated sources, right? So that term deals with that. So that's the equation. And what's important is that you understand the physics of what each term represents. Any question here? And this is the equation that Monte Carlo simulation solves. I want to be very clear about that. This is what the Monte Carlo simulation does. Simulates this equation. Okay. So just a couple of reminders. Transport coefficient is mu s plus mu a. Phase function is this angular density function. You can have volumetric sources. Okay. You'll see this again. But yes. Steradian, we're going to see it right now. Okay, and bear with me for a couple slides and then we'll get there. Mm-hmm. Yeah, so think about it this way. Even power, if you think of watts, what is it? It's joules per second. Joule is basically number of photons, right? So you always have a rate at which photons are going. If you have a steady source and you generate this temporally static light field, then everything is in steady state. But if you have a temporally modulated light source, I don't know if maybe some of you are familiar with temporal frequency domain or photon density waves, where you actually inject light into a material, but you intensity modulate it at megahertz frequencies. Then the light field that is in the tissue is actually pulsating, okay, with time. So typically the time rate of change happens because you're driving the system at some sort of temporally oscillating sort. But there is, strictly, if you want to model it on very short timescales, there is a time between when you start to turn on your laser and when that steady state light field is established. That happens very quickly because the speed of light is so fast, right? Okay. Does that address your, okay.
Dynamic scatterers and optical properties also.
Yes, but that's because mu s is fluctuating as a function of time, right? Right. That arises because, yeah. So it could either be the source of the light that's changing with time, or it could be your optical properties, or the spatial arrangement of scatterers is changing with time. Yeah.
So you can have a version of this equation independent of time.
Yes, absolutely. Yeah. Yeah.
Time
Just remember that and then.
derivative.
Yes, absolutely. Okay. Good questions. Any other questions? Yes. Yes.
It doesn't scatter.
Yeah. Yeah. So in a purely absorbing medium, right, the angular distribution of light never changes. Right? Right. You have to have scattering in order to get angular distribution. Yeah. Angular variation. Okay. I told you that you can deal with polarization. I won't dwell on this, but the Stokes vector down here, I, is a way to, in the transport context, fully characterize the parallel and perpendicular components of scattering. The star refers to the complex conjugate. And basically, you're replacing the radiance L with the Stokes vector I, and you have the same equation. The challenge is that you have a different phase function for each Stokes vector component. So this is so you get a scattering matrix instead of a phase function, and this is a gnarly equation to solve, but people do it.
What's the reason you do this one instead of the other?
If you're putting in a polarized light source into your medium, and you have there's certain molecules like glucose, I believe, that actually have preferential rotation of the optical field. And so if you send in light with different polarizations and you detect the light, even though they're scattering there at those different polarizations, you can then infer potentially the concentration of these molecules that have strange properties in terms of how they interact differently between parallel and polarized light. So there's a whole bunch of kind of polarimetry applications in turbid media that
That's kind of location based too, with how the particle is rotating.
yeah, no, so there's some molecules that are isotropic, but their intrinsic way that they interact with light is different based on polarization. But yes, so we don't deal explicit, but you're right. Maybe that's one thing I should mention is that this phase function, or in this case, the scattering amplitude matrix, is generally is a function of both polar angle and azimuthal angle. That's a very difficult problem to solve. And actually in our field, typically we assume azimuthal symmetry in terms of particle scattering, meaning that we assume naively that all scatterers, you can pretend that they're spherical scatterers, that their scattering distribution is only dependent on the polar angle and not on the azimuthal angle. But strictly, if you have a way of doing it mathematically in the radiative transport equation, you can deal with azimuthal variations in scattering. But just in our field, we typically assume the scattering is azimuthally uniform. Yes. Yes. I'm not that well versed in the Stokes vector, to be completely honest with you. This is kind of apparently, if you can solve for each of these four components of the Stokes vector, you have a complete description of the polarization state of the wave. And I don't actually know the history. There are actually different vectors you could use. There's like a Jones vector. There are different representations of how you can come up with four components that are independent of each other, but when combined, give a complete description of the polarization of the light field. But I'll tell you, I'm not an expert in that domain. There's this thing called the Poincare sphere, which describes circular, parallel, and perpendicular polarizations, and there are various ways you can come up with a vector that describes a general polarization state. That's as far as I know. But
Q looks like the degree of linear polarization is maintained, right? I don't know if that's true or not.
yeah, I'm not sure, to be quite honest. I think this I is somehow the total intensity. This is this is right. And then this has to do with crosstalk. You know, when you have if you're irradiating something with parallel light, can it become perpendicular and vice versa? And then this has to do something with phase. I'm not sure exactly. All of that could have been wrong. Okay. It's just complete speculation. Okay. But I just wanted to let you know that, and there are, I think Jessica Romello-Roman at Florida International University, she's developed Monte Carlo codes that explicitly deal with polarization. And Min Zhu, I believe, also in New York, Hunter College. Yeah. So there are codes out there that deal with this and use. Okay, so there's a question about 4 pi and what's the steradian and things like that. So let's go. So again, very few people are interested in the radiance explicitly, but I think it's very important to understand the radiance conceptually. But what most of you are probably familiar with is fluence rate. which is the total amount of light emitted from a given point. So if you have the complete solution to the radiance, you can get the fluence rate by integrating the radiance over the entire unit sphere. And sometimes you see that as the surface as 2, which is basically a unit sphere, or you see 4 pi steradians. And so you want to integrate this over all 4 pi steradians. So how is that done? Okay, we go to our old friend spherical coordinates. So I'm a simple-minded person. What I always think about, so you have 2 angles that are of importance: the polar angle, theta, and the azimuthal angle, phi. I always think about it because I loved looking at globes when I was a kid, right? Theta is latitude, right? So theta equals 0 is the North Pole. Theta equals pi is the South Pole. Theta equals pi over 2 is the equator. Okay, that's how I think about it. And azimuth is, is longitude, right? You start at the, Greenwich Mean Time, and you go to the international date line, and then you come back around, right? So what we need to do is that we need to integrate over the entire unit sphere. So, well, how do we do that? Well, we know that when you're close to the North Pole, to go around the entire globe it's a really short path, right? But if you're around the equator, you're taking a really long path, right? And that's given by sine theta, right? The distance away from the North Pole, in some sense, you are to take a round trip depends on that polar angle, right? If you're right at the North Pole, you just you turn around in a circle. Okay, I've done the circumference of the globe, right? So this path is given by sine theta d phi, right? Okay, and then this arc is just given by d theta, right? So what you integrate is you do sine theta d phi d theta, right? So sine theta d phi is going around the world, and d theta is just going from 0 all the way from the North Pole to the South Pole, right? And so we integrate theta from 0 to pi, that's from the North Pole to the South Pole, and then for each theta, you go around the world, 0 to 2 pi, okay? And so that's your integral, okay? And the reason why we say 4 pi is that if this is 1, you do this integration, you get 4 pi back, because the surface area of a unit sphere is 4 pi. Okay? I went through that maybe pretty fast. Any questions about that? Okay, and so this is really important in terms of internal light fields, right? We talked about therapeutics or fluorescence, right? Ultimately, if you're trying to create a temperature change or you're trying to excite a fluorophore, the fluorophore doesn't care what direction the photon came from, right? If it's absorbed there, it makes no difference, right? You just want the total light impinging on that location. The temperature change is going to be the same whether the photon came from one direction or the other and gets absorbed there, right? So you really don't care about direction. You just want to know what is the total amount of light that's available at that point. Okay. Now, it's different for reflectance or transmittance. So let's think about a light field emanating from a point here. I put it right at the surface, but you actually have a slightly different light field inside the tissue than outside because you may have a refractive index mismatch. So there's actually discontinuity in the radiance if you look at the light inside the material versus outside if there's a refractive index mismatch. And if you are interested in reflectance, you're not interested in the whole surface of the sphere. You're just interested in this hemisphere. Okay? So here I denoted the z coordinate as positive going into the tissue. So we're interested in the negative z space, right? So I want to integrate the unit sphere only where this space is negative, right? So this is basically integration over a hemisphere, okay? And I'm interested in the radiance of the light coming out, not at 0, because 0 is a discontinuity. You want to look at an infinitesimal location just above that boundary, and you want to look at the emission of light on the other side of that boundary. And typically we have planar detectors, right? We don't necessarily have a detector that is that is shaped hemispherically. So you actually have to take the projection of this light onto the unit normal of that detector. And so that's what this minus z dot omega is. So you take the radiance, that exists on the other side of this boundary, and you have to take a dot product of that relative to the unit normal in the minus z direction. Okay, and why you need that cosine, it's basically a cosine correction, is that if you have a certain amount of photons coming here, basically all of it will get tallied. If, depending on the numerical aperture of your system, if you have a photon just grazing that detector, it's not going to register as much, just like a solar panel is not going to capture much light when the sun is setting, right, as opposed to high noon. Okay, so that is just a cosine theta correction. And the integration is done the same way. So you only integrate where omega dot z is negative, and you have integration from, in this case, pi over 2 to pi in theta, and again, 0 to 2 pi there. Okay, so that's how you would compute reflectance from a solution to the radiance. Okay, so that's the end of modeling for today's lecture, at least. Now we're going to talk about optical properties and where they come from. Any questions? Yes, Najib. Yes. Say this again, I'm sorry?
Is the detector part of
Yes.
the equation, is it the minus z?
Yes. So imagine you have a detector here, right? And it can receive light from multiple angles, right? So essentially the amount of light that crosses the boundary is linked to the cosine of the angle of the light impacting that surface. It's just like say in fluid mechanics, if you're looking at the flow across a boundary, if you have a flow at a grazing angle, only the component of that flow that is orthogonal to that boundary comes across. It's the same thing with a photon. Okay, is that okay? Okay, yeah. Okay, so let's talk about scattering and absorption properties. It's a beautiful diagram developed by Steve Jacques a long time ago. He's published it in many different places. I like this one that just happened to be on the web and not in a publication. So it really shows you kind of, we tend to probe tissues using light in the visible or near infrared, and you see this kind of range of spatial scales that are relevant to probing cells and tissues across 3 orders of magnitude, going from lipid bilayer membranes on the order of tens of nanometers to variations in refractive index and collagen, which tend to be ordered between 60 and 70 nanometers. You have macromolecular structures that are on the order of tens of nanometers. You've got organelles that are on spatial scales hundreds of nanometers, mitochondria on the order of a micron or so, collagen fiber bundles. You have both striations and collagen molecules order on the tens of nanometer spatial scale. You have bundles of collagen that tend to aggregate on the micron to up to 3 micron spatial scale. Nuclei within cells approaching 10 microns on cells themselves. So all of these structures have variations in refractive index, and it's the variations in refractive index that give rise to scattering. And again, so you have this happening on very spatial scales, and the size of the scatterers has a profound impact on the spectral variation of scattering as well as the angular distribution of scattering. So typically when we consider structures that are much smaller than the wavelength of light, the term that's often used is this is Rayleigh scattering. And we'll talk about what Rayleigh scattering is, but typically the kind of the thing that we often talk about is the spectral dependence. And when you have structures that scatter light, but they're very small compared to the wavelength of light, the spectral dependence is very steep. It's like 1 over lambda to the 4th. Once the spatial scales of the particles start to become comparable to the wavelength of light, the power law tends to become much more gentle. And, in the range where you have scatters that are larger than the wavelength of light, it tends to be on the order of 1/λ. I mean, there's a lot of variation there, and it's not a sharp cutoff. It's a continuum. And so you have cellular structures and extracellular structures. So these are pictures of collagen, where you have this banding structure due to the repetition of certain protein residues in the collagen fiber. It tends to be actually very tightly organized, especially in the cornea, like 64 to 68 nanometers. And then the bundles themselves aggregate on the micrometer spatial scale. So all of these give rise to very unique features in scattering. Okay, so let's talk about scattering from a more fundamental perspective. So, the classical framework in which we think about scattering is Mie scattering, the kind of, I lied to you, there are more equations. So sorry about that. So the way that we think about it conceptually is that we have a scatterer here. We have a plane wave coming up bottom to top. This plane wave has polarization. It could either be parallel polarized, so this is the incident field, the parallel polarization component and the perpendicular polarization component. And it encounters the scatterer. This scatterer will modify the angular distribution of the light emitted from that location. So even though you're coming in at a well-defined theta, you will redistribute that light in angle, and it will be emitted as a spherical wave. And this is the classic spherical wave propagator. And that's your scattered field. Your scattered field is basically, and this is called the scattering amplitude matrix. It's very specific to the refractive index of the particle, the size of the particle, and in a general case, the shape of the particle. And I kind of simplify things here. Technically, this should be a function of location as well. Because as I said earlier, actually the scattered wave evolves with space, but I'm just going to consider the far field distribution. In that case, the spatial variation doesn't change. And you can calculate the scattering amplitude matrix using Mie theory. And actually, my colleague, Jonica, has put together a beautiful tool and with a beautiful GUI, and you're going to be able to visualize these things for particles of different sizes and particles and using different wavelengths of light. But essentially, the elements of the scattering amplitude matrix are dependent on particle size, shape, and relative refractive index. Okay, so that's fine. We're not going to go into the weeds there. But what's important about this is that from such an analysis, you can get metrics that lead you to the scattering coefficient. So let me just describe that. First, in Mie theory, there's a fundamental metric called the scattering cross-section. And so the way that you compute scattering cross-section is that you have a plane wave incident on a particle, and you detect the scattered light in a detector, and that detector is goniometrically rotated around the particle. So you get the amount of scattered light at every angle. And you take the ratio of the scattered light, the intensity, electric field square, divided by the incident light, and you integrate that over all solid angle, over the all 4 pi. Okay, not only in the plane, but outside. And that is called the scattering cross-section. And it's also, you can refer to this as the scattering efficiency times the cross-sectional area of the physical cross-sectional area of the particle. But basically, this has units of area, okay? And so you have units of area for one particle, but of course, in a tissue, you have many, many particles, right? So the actual scattering coefficient is a product between this scattering cross-section times the number density of scatterers, number of particles per unit volume. So you have an area here, and then this is a density, a volumetric density, so you get units of inverse length, okay? And that's where your scattering coefficient comes from, okay? So if you know number density of particles, you know the size of the particles, you know the refractive index, you can compute the µs, okay? And you can compute the spectral dependence of µs. And then as I mentioned, the reciprocal of µs represents a scattering mean free path for photon travel in that medium, okay? So you can do this for polystyrene spheres. A lot of people in some labs, to calibrate their instrument, they use like a standard turbid media, it could be polystyrene spheres, it could be intralipid, it could be lots of different things you can use. Okay, so let's talk about me scattering versus Rayleigh scattering. Richard is not here. Okay, that's strange. I don't know what to do here. Can we flag Richard, or do you know what to do, Bernard? I don't want the display to turn off.
I can guess, but I don't prefer it.
Well, I don't know anything, so it's better than me. I'm sharing.
Yeah.
I'm gonna want to turn off the TV.
Yeah,
I wonder if you unshare then share it. No.
you can try.
Maybe share. That was, I don't know if it's waking it up.
That doesn't, that I think. Idle display power off. Soon turn on by, press a button, press any button. So press a button or press a button. Oh, there you go. Okay, you did something,
I
Bernard.
just did channel off.
Excellent. Thank you. Okay. So, so we're really interested in the angular distribution of scattering and the spectral variation in scattering and the size. So this is a really cool, I've always thought this is a cool plot. This is the angular distribution of scattering of a water droplet that has a diameter of 20 microns in the atmosphere when irradiated with red light. Okay, this is a polar plot. It's on a, sorry, the resolution is, it's on logarithmic scale. Light is coming from left to right. And you see some really interesting features. Number one, you see that this is logarithmic scale. So this every concentric circle is 1 decade drop in your intensity. Basically shows you that most of the light is basically going directly forward with some slight angular deviation. And then you get a drop off of 2 orders of magnitude, and then you get this background. So there's light scattered in other directions, but it's much smaller, 100th, if that, or 1,000th of what's going directly forward. But you have this really intriguing angular structure, okay? And so intuitively, why this angular structure arises is you really think about what I said earlier about the spatial scale of your object and the spatial scale of the light itself. So if you think about a 10 micron object and you have a wavelength of 650 nanometers, if you we don't have a blackboard here, but if you think about superimposing a sine wave with a period of 650 nanometers onto a 20 micron object, different locations in that particle are going to be experiencing either a trough in that electric field or a peak. And that's, of course, and it's propagating through. So what that's happening is that the light is exciting dipoles within that particle, and each of these dipoles are oscillating at slightly different phase relationships. And so and all those dipoles are radiating. So you can imagine that in one angle, you may have destructive interference, whereas at another angle, you can have constructive interference. And so this angular noise is not noise, but really a sum of the radiation of light from all of those dipoles, each of which are oscillating in slightly different phase relationship relative to each other. Now, what happens is that if you either increase the wavelength or reduce the size of the droplet, you'll get fewer and fewer ripples because you're going to have fewer number of dipoles in that particle, and you have less structure in that constructive and destructive interference. And then when you get the particle really small, you just have one dipole. And all of that structure is lost. And that's what Rayleigh scattering is. The particle is smaller than the wavelength of light, and it basically radiates like a single dipole. And radiation by a single dipole is very simple, just it is dependent on the polarization of light. But essentially, perpendicular polarization, you get this lobed structure, equal amounts of light going forward and backwards, but you have some angular variation. And then if you have perpendicular polarization, it's actually completely isotropic. And this green is basically, if you have unpolarized light, you have equal amounts of parallel and perpendicular polarization, you get that distribution. Okay. So I guess I kind of glossed over a few things here. For these large structures, there's a paper by Graf that did a correlation for me particles of a population of me particles. You get this, 1 over lambda to the 0.37. Your scattering cross section is linearly related to the particle size and the relative refractive index. I'm sorry, this is the refractive index of the particle, and m is the relative refractive index. That is the refractive index of the particle divided by the refractive index of the medium. And and we talked about the angular distribution. And then for Rayleigh scattering, the scattering cross-section is highly dependent, strong dependence on the radius of the particle, and inversely proportional to the fourth power of lambda. Yes, Najib. Yes, sorry.
You have an idea of like two angles that have a sharp intensity drop?
It's very particular to that wavelength and that size. And actually, you'll get an opportunity to play with a tool where you can actually have particle of a given size and refractive index, and you can have a wavelength slider, and you'll see it's just very particular to that combination. Yeah. So you have very strong destructive interference at those two angles, right? Yeah. Yeah. Other questions? Yeah, it's actually quite mesmerizing. With Jonica's tool, you have a given, what is it? The slider is for wavelength, right? Or is it for size? It's not for wavelength, I think. Yeah. Yeah, this is on log scale. Yeah. Yeah, if you do it on linear scale, it'll actually look quite smooth. Yeah. Okay. So let's talk about scattering in tissue. This is all nice, but that's what happens when you have a single type of particle with a single type of refractive index, a single size. Reality in tissue, you've got scatterers of all sorts of different sizes, all different relative refractive index. And so we need to parameterize, in some sense, the scattering properties as a function of wavelength. And another thing you have to understand is that Rayleigh scatterers, like I said, you get equal amounts of light scattered pretty much in all directions, in forward hemisphere and backward hemisphere. In me scattering, you get most of the light traveling still in the forward direction. So remember how I mentioned earlier going from the transport regime to the diffuse regime. And what the key element there is that you lose directionality. So if you have a particle that's basically scattering light directly forward, that's not really effective in randomizing your direction, is it? Right? Because it takes, you look at that water droplet, right? 99% of the light is basically being deviated by what is that? 2, 3, 4 degrees, right? So you can imagine that light needs to interact with maybe 100 droplets before it loses directionality. But if you're interacting with a me scatterer, maybe only a few, right? Because you're really redistributing light angularly. So looking at mu-s by itself is not a particularly useful metric to understand how far light has to propagate before the directionality is lost. What is what's called the reduced scattering coefficient. And this is what we do, is that we multiply mu-s, which is the density of scatters in the medium, times a parameter called 1 minus g. G is called the single scattering anisotropy, or the scattering asymmetry in the medium, and it's the average cosine of the scattering angle. So if your scattering angle is only 1 or 2 degrees, your cosine theta of that is 0.99 something, right? But if your average scattering angle is essentially 90 degrees because you're redistributing light over all angles, G is 0. So if you calculate mu-s prime, that's a better parameterization or understanding, gives you better understanding of how effective a scatterer is in redistributing light angularly. And you can, and so that's, so often in our field, we look at mu s prime as opposed to mu s. And the spectral dependence of scattering, typically we represent it as a power law. A simple power law is just using, a lambda to the minus b power, where a is the amount of scattering and b gives you the spectral dependence. Or you can say, well, I have a tissue and I have some fraction of scatterers that behave like Rayleigh scatterers that go as 1 over lambda to the 4, and the remaining fraction that behaves as me scatterers. And so this is a more kind of sophisticated parameterization for reduced scattering. And then you can look at the interplay of whether you really need this more sophisticated formulation versus this basic formulation. So in cases where the B value you get from the simple formulation is identical to the B value here, it means that the Rayleigh scatterers are not important. And that's these tissues here. But the tissues here, if you have a lot of Rayleigh scatterers, that means that B me is going to be larger than B because you've taken all the Rayleigh scatterers out. And so, I'm sorry, B will be larger than B me, and you'll get something like this. So this kind of tells you what, look at this paper by Jacques, which is in your references, tells you the tissues where you really need to consider the Rayleigh scatterers in order to get a good representation of the spectral dependence of scattering in those tissues. And then you've got tissues of different types in terms of this A value. So, skin and epidermis, they're notorious for scattering light, but things like breast, liver, and muscle, their amount of scattering is much reduced relative to skin, for instance. And then these are plots for your reference in terms of this variation of this single scattering anisotropy G, which is important in terms of the directionality of the light field. Absorption, and then we're done. I know people are fading. Yes, Hector.
Back to the last slide.
This one?
Yeah, what's lambda zero?
Lambda 0 is just a parameterization. You can choose it wherever you want it. Basically, it just tells you that add lambda equals 0, the mu s prime will be A.
Yeah.
Okay, and so it depends. Exactly, and often you maybe make measurements on multiple wavelengths and you want to fit it to a power law, and so that allows you to anchor it where you want. Often you do it at a midpoint over your spectral range. Yeah. Okay, optical absorption. One thing you need to really be careful about with optical absorption, at least looking at parameters in the literature, because chemists and physicists use different conventions. So chemists, tend to do the spectrophotometer, the transmission of light through absorbing liquid, is just the ratio of your measured intensity over your initial intensity, and then they use base 10. So they say, well, this is 10 to the minus rho, where rho is called the optical density. And rho is the product of the molar extinction coefficient times the concentration times the optical path length. Okay, so if you look at molar extinction coefficients, you're able to get the absorption on a concentration basis. Now physicists tend to use base E, and they parameterize the same transmission in terms of a absorption cross-section times the number density of absorbers. And as a result, this product, omega A and L, is not the same as epsilon CL because they're using base 10 versus base E. So when you get molar extinction coefficients from like chemical handbooks, you have to divide that by the natural log of 10. It's like a factor of 2.3 or something in order to convert it to mu A. Okay, so just be aware of that. We'll go through the math, but basically this equals this. So then you take a natural log of each side, and so it's minus mu AL is equal to natural log of 10 times ECL. Okay, and then you've got to make sure you You multiply by 2.303. And then the mu A again represents the mean free path of photon travel is absorption. Okay, home stretch, I think 4 more slides and we're done. So optical absorption of tissue varies quite a bit. In the UV, you get actually huge absorption by water below 200 nanometers. And then you start to get absorption of water again once you get beyond about 1.5 microns. But in this window here, we don't have to worry about water so much, but we've got to worry about blood. Okay, and blood absorbs quite a bit in the blue-green. It drops off tremendously as you get into the red near infrared. Water, I didn't show lipids. Lipids also start to percolate in around 900. But this is, what we call, kind of the therapeutic or diagnostic window in the near infrared going to the SWIR. Melanin is definitely, if you're looking at skin, is an important absorber you have to consider. But this gives you a sense of what are the various constituents you can probe. The thing also that we're very interested in is what is the ratio, the relative prevalence of absorption relative to scattering, because that tells you something about whether you can approximate the radiator transport equation with the standard diffusion approximation. So here in tissue, I've plotted the ratio of scattering to absorption as a function of wavelength. And so here you see this window between 600 to about 1200 or so, where your scattering of light is about 10 times more prevalent than absorption. And in those cases, you tend to be able to use the diffusion approximation. You don't have to do the full RTE in many cases. But once you get below about 10, then you really need to deal with Monte Carlo. Unless you're highly absorbing, in which case you could just use Beer's law. You don't have to worry about scattering at all. And certainly for therapeutic applications in the infrared, say in 2 microns or above, you probably don't have to worry about scattering much at all. So this is an important graph to kind of think about in terms of light transport and what model you may need to use depending on if you're in the transport or diffuse regime. Okay, and then this is pretty much the final slide. So I talked about spatial scales and time scales, and so this is very important. So we talked about what are the range of properties for mu A and the range of properties for mu S. And here I'm just limiting ourselves to the visible or the red to near infrared. So the typical values for absorption, I mentioned earlier, the reciprocal length scales are on the order of 10 to 1,000 millimeters, out to a meter. So that tells you that light has to propagate quite a bit before it gets attenuated. But the reason why you're able to measure absorption is because the multiple scattering gives these photons a very tortuous path through the tissue. So even though you may be measuring the transmission of light over only a few millimeters, the path that the photons took to go from those few millimeters is probably tens to hundreds of millimeters because of all the scattering events. And so that's what gives you the sensitivity to absorption. The challenge also is that you really need to know that path length, and that path length really depends on the amount of scattering in the material. And so those spatial scales are on the order of a micron to about 100 microns. And then for attenuation, we really look at the transport mean free path, which is the total attenuation coefficient, the reciprocal of the total attenuation coefficient with mu s prime as the characteristic scattering length. What's also interesting is these spatial scales give you time scales, right? Because if you know these distances you need to travel, it takes a certain amount of time for that travel to occur. And the reason why these temporal scales are really important is that there are techniques like temporal frequency domain imaging where you're intensity modulating the light. And the rate at which you intensity modulate the light gives you sensitivity to absorption versus scattering. These spatial scales are also important because, say, in spatial frequency domain imaging, the spatial modulation of the light is tuned to the spatial scales for transport. So you're going to see how the domains in which these techniques work well versus not so well are actually intrinsically linked to these temporal and spatial scales. These are just for your reference because you're going to see these terms if you probe the literature there are various metrics that people use. And I'm going to end there and end with my teaching objectives. And people probably need to stretch a little. And so thank you for your attention, and I'm happy to address any questions. Please. Okay.